orbitals, and we've been talking about how orbitals contribute to bonding, and now we're going to continue with that concept of bonding and electrons, and we're going to look at not just how things bond, but what the shape of the molecule is once the bonding has happened. So we're going to have geometry meets biology meets chemistry. It's all kinds of things together as we're going to be talking about the shapes of these things and how that impacts their function. So lots of different ideas will be combined here for this. If you just okay, so the things we're going to be talking about are from a theory, which when we're in science class, the word theory means we're not sure about it. No, just kidding. The word theory means that we have done a bunch of testing and we think that this is a very good picture of reality. So the Vesper theory, Vesper valence shell electron pair repulsion theory. And so what they're talking about here is that electrons repel each other. So remember, the electrons are negatively charged, the nucleus is positively charged, which is why the more electrons you have in the electron cloud, the more it is attracted to the nucleus and the smaller the atom gets with regard to its radius. But the electrons being negatively charged are also repelled by each other. So if Alec and Lavilla were electrons, they would be wanting to be as far away from each other as they possibly can. But if Steph were a proton in the nucleus, they would like to be as far away from each other as they can with also being as close to Steph as they can, right? So electrons don't just leave the atom and be like, yeah, peace out, I'm out of here, too much negativity, right? No, because they are attracted to the nucleus. So they stick around the nucleus, but they want to be, no, give me my space with regard to each other. So they space themselves out to be as far away from another electron as they can, while still being close to the nucleus, okay? So that creates bond angles. If it takes two electrons being shared to make a covalent bond, those two electrons have to be somewhat close to each other because they are constituting a bond. But they want to be a long ways away from other pairs of electrons that are making a bond. And they would rather not be, right next to other electrons as much as possible. So if you have a sphere and you've got a negative thing over here and a negative thing over here, they will find themselves exactly opposite each other. If you have three things around a sphere, they will be, like a peace sign, so that they're as far away from each other as possible. You have four negative things, then it looks kind of like a jack, like that game that you played called tetrahedron. And the more sources of negativity, the more points of negativity you put on that sphere, the more complicated the geometry gets. And so we're going to be looking at bond angles and shapes of electrons, but it's all tied to this idea that electrons want to be as far away from each other as they can, while still being close to the nucleus. Okay? So electrons are like these three knights in the Monty Python and the Holy Grail. When it comes to each other, they want to be as far away from each other as they can, and they see another electron and they're say, run away! You guys seen that movie? You know what I'm talking about? Monty Python and the Holy Grail.
Is that like a parody?
Oh yeah, it's a big time parody. Only one person has seen it, you don't get the joke. Okay, you need to go see that movie. It's hilarious. 1980s humor, British humor, but it's great. Okay, anyway. So we're going to continue with this. You can take a moment to write this down. So when you draw Lewis dot structures of atoms, that's why we had you do that first, you are aware that we have pairs of electrons, and then there are bonds that come out of the central atom too. And so we're going to base all of this on Lewis dot structures. Most of the time, you're going to have four things coming off the central atom, either a pair of electrons or bonds. And so most of the time we have some variation of this shape called a tetrahedron. And that's what this looks like. And if you remember back in the days of geometry, a tetrahedron is a polyhedron with four sides. If you played role-playing games and you ever threw those like pyramid-shaped four-sided die to determine something, that's the shape of a tetrahedron. So the central atom is in the middle, and it has four things coming out of it. and they are either a pair of electrons that are not bound or a bond to some other atom. And so we draw it like this. The straight lines represent things that are in the same plane as the central atom. So you can take any 3 points and make a plane. So the central atom and the thing above and one of the things below we will say is in the same plane. And then they draw one where the line gets bigger as it comes out towards this thing, and that means this comes out, this sticks out of the page, sticks out of the plane, coming towards you, right? And then the other one they draw with hash marks to show that it sits behind the page, behind the plane. It's going away from you. So if you ever played jacks as a kid where you threw those things and you bounced the ball and tried to pick them up and catch the ball, right? Those things that you threw are usually tetrahedral shapes. Or if you watch, you know, probably cops and robbers kinds of movies where there's a car chase and the bad guy's car releases like spiky things into the road and the cops' tires get popped. Have you ever seen those? I don't know, it happened at Night Rider, a bunch of Dukes and Hazzard and things like that, right? Maybe Batman, yeah, too. Those things that you can throw on the road and there's always a spike sticking out are tetrahedral shapes. So whatever helps you identify this shape. 3 things line a plane, one comes out and one goes back. And the bond angle on a tetrahedron is 109.5 degrees. So if you measure from here to here, or from here to here, or from here to here, any 2 bond angles, you will see that it's 109.5 degrees. And that's the farthest away that 4 things can be from each other oriented around a sphere. And so if B were any further away from this B, then it would be getting closer to these ones. So 109.5 is the angle that you find on these tetrahedral shapes. Sometimes you'll see a little bit of variation with that depending on what is joined over here. Sometimes it's an atom with a very high amount of electronegativity, and so it pushes the other things a little bit further away from it. But generally speaking, 109.5 degrees is the angle you find. Okay, so here's some examples. This is methane. And methane has a central carbon and 4 hydrogens, CH4. And so you'll find that 109.5 degrees in the molecular shape of carbon. And this is just another example of that blown up a little bit bigger. So you can see central thing and 4 other things around it. Could be unbound electrons, could be an atom that it's bound to. Okay? And so we see that tetrahedral shape over and over and over again as we're looking at molecular models. Sometimes the central atom doesn't have 4 other atoms bound to it. Sometimes it only has 1 or 2 or 3 other things bound to it, but we still find that 109.5 degree angle. And so this is an example here of ammonia, NH3. And if you were to draw the Lewis dot structure for NH3, you would have N in the middle, and then you would put 2 dots because the nitrogen has 2 unbound electrons, 1 free pair of electrons. And then around it, the other 4 positions will have a hydrogen covalently bound with the nitrogen. And so what you see is that the sodium has 1 pair here of electrons that are just nitrogen's electrons. And then the other 3 hydrogens have covalent bonds. It still arranges itself in a tetrahedron, though, because the electrons associated with this bond still want to be as far away as they can from these electrons up here. So they still push themselves into this tetrahedral shape. It's just that we have only 3 bonds, and the 4th position is an electron pair. So we call this a pyramid, a tetrahedral pyramid, because it looks like a pyramid with just this pair of electrons floating up in space. Okay? Now you can imagine in your mind's eye, I'll show you pictures in a minute, that if this other hydrogen were to be replaced by just a pair of electrons, then you'd have a pair up here and a pair down here, and you'd only have 2 of the bonds, or 2 of the positions represented by a bond, and then you'd have this thing that looks, I don't know, looks like a boomerang, kind of, and we call that a bent 109. And so that's, again, just a bent molecule, but you still have that 109.5 degrees here, because even though there's only 2 bonds, they can't push each other further away than 109.5 degrees, or they start to encroach on these other electrons up here. And if you even have only one bond, and the other three positions are all electron pairs, now you have a linear molecule, a molecule that's just straight, right? There's only two things, it's a straight line. But if you were to look at where are the electrons around that other atom, the electrons will still arrange themselves in a tetrahedral shape. So that tetrahedral shape is always there, almost all the time. It's just, the question is how many electrons and how many bonds are there that make up those four positions. So some more pictures. This is a picture of a pyramidal molecule, and it has three atoms bound to a central atom. But the reason that it's not a flat shape is because there's still a set of electrons up here, and so they still push themselves away. Okay. OF2, oxygen difluoride, would be a central oxygen atom and two fluorines. But then you see that oxygen still has two more pairs of electrons here. And so it still pushes itself into this tetrahedral shape. It's just that two of the positions are taken up by electron pairs, not by bonds. Okay? And the water molecule, the most most famously drawn or commonly drawn molecule that you've probably seen, is a tetrahedral where oxygen, again, two bond angles to two hydrogens, but the other two are still out there, so it's still the same shape. Okay, and then diatomic fluorine, if you were to look here, still has four positions around it, even though there's only one bond. So the arrangement of these electrons around the fluorine would still look like a tetrahedron. Okay, even though it just looks like a Smurf butt in reality. Okay, there you go. Next slide. Okay, so we said almost always there are four things around the central atom, and so almost always it's some derivation of a tetrahedral shape. But there are examples of molecules where the central atom only has three things, and in that case it isn't a tetrahedron where there's four things around. It's what we call a trigonal planar, because you can put three things around a central atom in a three-dimensional shape and have it be flat. So picture like a steering wheel. It's spherical, and if your steering wheel had three spokes going to the center column of the car, the spokes would be flat and in the same plane as the points around the circle, right? You don't have a a three-dimensional shape with only 3 points. Anytime you have 3 points, you have a plane. And so this is called trigonal planar. Trigonal meaning there's three things, planar because it's always in a plane. And here we don't have a 109.5 degree bond angle, here we have a 120 degree bond angle. And so it would look like this, where all three things are in the plane, and it's 120 degrees between any two items. There are examples where the central atom has only three bond angles, and only two of them go to an atom, and one of them is a free electron pair. That would also be bent, but it's bent with a 120 degree angle, so we call it a 120 bent or a bent 120 instead of a bent 109. The difference is the central atom supporting 3 regions of electronegativity or 4 regions of electronegativity. Okay, and then there are linear atoms or linear molecules as well, where the central thing only has one other atom and the other two positions are just electron pairs. So the molecule looks like a straight line, and the other two positions are just electron pairs. Okay, more often than not, you get this 3 regions of electronegativity because of double bonds. Carbon always has 4 things coming off of it. But what happens if 2 of those things go to the same other atom? So it's a double bond. Now you only have 2 other things dangling off of carbon, right? And so more often than not, you get this kind of geometry because of double bonds, not because the central atom only has 3 valence electrons or something like that. So some pictures here. This is an example of a trigonal planar, where the central atom has 3 regions of electronegativity, and again, usually because one of those is a double bond. And so all 3 things around it, either electron pairs or other atoms that it's bound to, are flat, like in this 3-pointed star. Okay? An example of that is boron hydride. Boron is one of those weird atoms that are okay with a different number of valence electrons. Most of the time that's not true, but boron can be happy only looking at 6 electrons. So boron looks at 6 electrons and he's fine with that. He doesn't have an extra floating pair of electrons out there. 3 bonds going to 3 different hydrogens. And we have a trigonal planar molecule. Okay. Or more often, this example here, where you have a carbon double bonded to an oxygen, and then 2 hydrogens. So there's still 4 things on this carbon, but 2 of them go to the same other atom. So all the electrons here are being forced to be next to each other because they're part of this double bond. So there's only 3 regions of electronegativity here. And so that central carbon would have a trigonal planar geometry. It would look like this, where there's 3 things off of the carbon. Okay? And then there are molecules where there's 2 bonds and a pair of electrons floating here by themselves. So this is a bent, and it looks kind of like the water molecule bent, but it's a bigger angle because there's only 3 things, not 4 things. So my picture's in the way. That would be an example of a 120-degree bent molecule. Okay? And in that example here, we have, again, water is drawn. And so water is not the same as this. Water is a trigonal planar bent. I'm sorry, water is a tetrahedral bent. And this is an example of a trigonal planar bent. So they look similarly, but the bond angle is different. Okay, another example. This is a trigonal planar. Nitrogen in the middle here has 4 things dangling off of it, but 2 of them go to the same atom, and so we have only 1, 2, 3 regions of electronegativity. It would have a trigonal planar molecule. Okay, not 180. Why did that? Oh, that's because it came down here. There you go. Next thing, almost done. So we talked about 4 regions of electronegativity. We talked about 3 regions of electronegativity, and now if there's 2 regions of electronegativity, well then it's a straight line. If you're trying to arrange 2 things as far away from each other as they can be, but still close to a central thing, you get a straight line. And so you have 2 objects trying to be far away from each other, and they wind up being 180 degrees away from each other. Usually this is because of double and triple bonds. Almost no atom is happy with only 4 electrons, and so you don't usually find only 2 regions of electronegativity without there being double or triple bonds involved. And so this is a straight line molecule, and you will see lots of examples of this as we get into organic chemistry, because double and triple bonds show up a lot. This is ethene, also called acetylene, and this is a very, very high energy bond here between these 2 carbons. It's a triple bond. So this carbon, looking at 8 electrons, but it shares 6 of its 8 electrons with this one other carbon. This carbon also looking at 8 electrons, but again, 6 of them shared here. So for this carbon, there's only 2 regions of electronegativity. There's the triple bond, and then there's the single bond with hydrogen. And same thing over here. There's a single bond with hydrogen and then a triple bond. So only 2 regions of electronegativity. Those things go as far away from each other as they can, and you wind up with a straight line molecule of the hydrogen, carbon, carbon, hydrogen. Okay, so this is, again, a very high energy bond, but it would look like this. Looks kind of like a spaceship traveling through space. But what we have here is a carbon and a carbon sharing 6 electrons between them, and then a pair of electrons going out here. And so this straight line molecule. This is another example, carbon dioxide. Carbon dioxide, 1 carbon, 2 oxygens. This carbon is sharing 2 pairs of electrons, 4 electrons with this oxygen, and again 4 electrons over here with this oxygen. And so the carbon here has only 2 regions of electronegativity, so those 2 oxygens move as far away from each other as they can, and you wind up with a straight line molecule. So carbon dioxide is linear. If you looked at the oxygens, though, the oxygen has this region of electronegativity, the double bond, and then it has two other unbound pairs of electrons. So the oxygen there is trigonal planar, right? The oxygen has three things around it, but the central carbon is linear. So you can see how a molecule can have multiple geometries depending on which atom you're going to look at. Another one, beryllium hydride. Beryllium is one of those strange molecules. He is okay with only 4 electrons to look at. And so beryllium is looking at all 4 electrons that it wants to, and 2 of them are shared over here, and 2 of them are shared over here. So it winds up being a straight line molecule. Okay? And I think this is your last slide. The last thing to talk about is polarity. We introduced the concept of polarity really briefly last week, but we're going to get some more detail on it now. So polarity is when the electrons are not equally distributed throughout the molecule. And that is because of differences in electronegativity. So something like fluorine holds its electrons very close to itself. Something like potassium would kind of hold the electrons at arm's length, holds them a little ways away. So if something with low electronegativity bonds with something with high electronegativity, the electrons spend more time around the more electronegative molecule and create something called a polar bond. It's not a symmetrical bond. And so we use this kind of neat symbol down here to say that the electrons tend to spend more time over on this part of the molecule, and this part of the molecule is more positive, so we cross the end of the arrow down here. So it's more positive down here because there's less electrons hanging out over here, and it's more negative over on this side because there's more electrons hanging out over here. And we use that delta symbol, lowercase d in the Greek alphabet, and we would say plus, again, to represent a partial positive charge, and a lowercase d delta negative to say partial negative charge. And then you may see this symbol drawn and a number put here, and they're talking about there the magnitude of the charge difference. How big is this charge difference? And if they do, they will call that value mu, the lowercase m in the Greek alphabet. So you may see the mu in there, you may not. You may just see the symbol, and that says this is more positive and this is more negative. A molecule can only be a polar molecule if it has polar bonds. That makes sense. You can't have bonds that are all uniformly the same distribution of electrons and have a polar molecule. The other thing you have to have that polar molecule is an asymmetrical molecule. So if the molecule can be folded and everything along all the axes are the same, then the molecule is not polar, because even if individual bonds are pulling really hard, they're balanced on the other side of the molecule by other bonds pulling the opposite direction. So they cancel each other out with regard to charge. So in order for a molecule to be polar, it has to be asymmetrical and there have to be polar bonds. Okay? So some examples here. Ammonia, NH3, is polar. And so you can see here that if you were to ignore the top part, the bottom part of the molecule is pretty symmetrical. It's a nitrogen and 3 evenly distributed hydrogens down there. But because it's not symmetrical with another hydrogen floating on top, it's an asymmetrical molecule. So then we could say, okay, it's asymmetrical. Is it polar? Are there polar bonds? And yes, the bonds that are present are polar, because nitrogen pulls on electrons a lot harder than hydrogen does. So the electrons will spend more time around nitrogen than they will spend around the hydrogens. So it satisfies both requirements. It's asymmetrical and there are polar bonds. So ammonia is a polar molecule. And we would draw the little symbol here saying that the top part of the molecule is more electronegative and the bottom part of the molecule is more electropositive. And in this particular example, they've given you a numerical value for the charge separation on that molecule. And so mu equals 1.46. Okay? Mu, yes. No, mu like the Greek letter M. And then I think in sliding things around, I lost my example over here, but this is another example where the fluorine pulls harder than the nitrogen does. So even though nitrogen is pulling against hydrogens, if there's a fluorine present, it pulls this way, so the charge is a different direction. It's still polar, but it affects our value for mu. Okay. Other examples. Here we have a carbon double bonded to an oxygen. This is fairly non-polar. These two things are really close in electronegativity, but then the hydrogens out here lose the war. The hydrogens lose their electrons to this region of greater electronegativity. So, and it's asymmetrical. It's not another hydrogen out here. So it's asymmetrical, and it is polar bonds with regard to the hydrogen carbon. So we would draw our symbol this way and say this part of the molecule is more electronegative. This part of the molecule is more electropositive. Here, the carbon loses slightly to the oxygen. It's very, very close electronegativity, but if you just had a carbon and oxygen, it's going to spend slightly more time with the oxygen. But because it's symmetrical, the slight charge going this direction and the very slight charge going this direction balance each other out. So this molecule is not polar because it's symmetrical. So anytime you have a symmetrical molecule, even if you have polar bonds, it doesn't matter. Symmetrical molecules are non-polar. So carbon dioxide, non-polar, mu is 0. There is no meaningful charge separation. Okay? One more example here. Here we have carbon with 3 hydrogens and then a chlorine molecule. Chlorine atom. Well, carbon pulls a little bit more than the hydrogen does, so the hydrogen's electrons spend a little more time around carbon. And then here comes chlorine with a massive electronegativity. So chlorine pulls even harder than carbon. So generally speaking, the electrons all spend more time up here than they will down here. So we would draw our symbol this way, saying electrons are more likely to be found up here, and this region of the molecule is more positive, and I don't know why my crossbar got not copied well, but this region is more positive, this region is more negative. And that is it. So molecular geometry, you'll be playing with this for the rest of this week, and for all of next week, we'll be building models and all that kind of stuff. So, any questions? All righty, there we are.